The rally car is fast, but speed isn't everything. This machine is built for trouble from the ground up. And when you see a cuckoo this big on a mechanical clock this tall, you gotta wonder what makes it, well, tick. The lift lock is a giant elevator that raises boats in a 2 million liter tub, all without gas or a motor. The web offset printer, high-speed printing at 20 kilometers per hour without a single smudge. Let's take a look inside these machines and see how they work. This is a rally car. It may not look like much sitting here, just a regular car with a few bells and whistles under the hood, right? Wrong. This machine may look like a Clark Kent, but once it's turned on, it's a supercar. The ride you pick up at the local dealer is related to the rally car, but we're talking distant cousins here. Really distant. In fact, the only thing that's left from your car on this machine are the lights. Turbocharger, big brakes, steering. It's all redesigned for speed, control, and handling. To beat an insanely difficult course without killing anybody. Let's see how it works. First, speed and control. Two things make that happen. The engine for acceleration, the brakes for taking corners and maintaining control. High-end rally car engines pump out over 300 horsepower. Thanks in large part to its turbocharger, which is basically a turbine placed in the car's exhaust. The turbine spins up to 150,000 RPM, 30 times faster than the engine. All that spinning powers a compressor that sucks in the air from outside, compresses it, and injects it into the engine's combustion chamber. More air means you can burn more fuel, with explosive results. And all that power shows up here at the start line, where it rockets the car up to 100 kilometers an hour in under 4 seconds. And that speed is great on the straightaways of a rally course. But these races are won and lost in the corners, where small mistakes cost valuable time. To master corners, this machine needs some serious stopping power. And it comes from some of the best brakes money can buy. Most cars have disc brakes with a single piston that move a brake pad onto a disc that slows the wheel. But they would literally disintegrate out here. A rally car needs as many as 8 to maintain speed and control. What about this challenge? A 180-degree hairpin turn. Top drivers make it look easy. A regular car and its driver? Not so much. Rally cars come equipped with a powerful handbrake that allows for this kind of action. You may use yours to park, but this machine's not built for standing still. Its lever sits next to the steering wheel, so the driver can grab it quickly. An independent hydraulic system locks the car's rear wheels, and around you go. Now that's what this machine is all about. It's also about staying in one piece. In a rally car, every seam gets a continuous weld, including the roll cage. This molds the body into a single unit, so on impact, the shock is evenly distributed. On top of that, the roll cage is structured with triangles directly to the frame. The cage is made of chromoly, an alloy that is lighter than steel and stronger too. The triangle design distributes force evenly, allowing it to withstand crushing blows from all directions. So not only does the rally car survive a rollover that would crush your average car, it recovers and keeps on going. The roll cage also provides a rock-solid base for the shock absorbers. Each has two key components, springs and dampers. They work together to absorb everything the road dishes out. The problem with springs is that they tend to expand as quickly as they contract, which makes for a very bouncy ride. The damper, a hydraulic chamber with a piston inside, controls the expansion and vibration of the springs, maintaining critical contact between the rubber and the road. Low and stiff for road races, high and loose for off-road. A set of 4 sets you back about 7,000 euros. But if you cheap out on the shocks, you'll pay a price out here. It's also all about staying on the road. The steering wheel is coated with a felt that locks in the driver's gloves like Velcro. You don't want to lose your grip out here. So rally cars are designed to keep control panels as close as possible to the driver. These paddles shift a gear in 50 milliseconds without the driver ever letting go of the wheel. And that's important because the difference between winning and losing a rally race is measured in fractions of seconds. When driver and machine get it done right, the champagne flows. If either slips up, the results are decidedly more painful. For speed, agility, and durability, nothing compares to a rally car. This machine may look like the one in the showroom, but don't go bringing your ride out here. This domain is reserved for the supercar. Welcome to Marienplatz Square in Munich, Germany. Home to a tower which houses one of the world's great mechanical timekeepers and a little number called the Glockenspiel. Its parts are spread out over 8 of this tower's 11 floors. Parts that include a bunch of these guys, a giant music box, a room full of gears, and 7 tons of bells. 100 years of gonging, cavorting, ticking, and talking. Let's see how it works. And let's start at the center of this machine with its amazing clock, which, like all big mechanical timepieces, is driven by a pendulum. Pendulums give us tick and tock, as well as the means to measure time accurately. But to do that, clockmakers have to overcome several stubborn challenges. The first is getting all of its parts to move at a precise unit of time that is repeatable, like 1 minute. So how do you get a minute hand to move precisely every 60 seconds? It starts with a little help from gravity, which gives the pendulum its perfect timing. You have to adjust its length until the swing lasts 1 second in each direction. That's it. The pendulum's weight doesn't matter. Gravity is constant. Neither does the distance it swings. All that matters is the length. And in order to work accurately, every pendulum is bolted to this, the escapement. As the pendulum swings past its center point, the escapement's teeth allow the gears to escape, one at a time. This creates a familiar sound we all know as tick. And as it swings back the other way, you guessed it, tock. Which leads us to a second challenge, how to beat friction that wants to stop the pendulum. After every tick and tock, the special shape of the teeth give the pendulum a very slight snap, which travels down its shaft. It's not much, but it's just enough for the pendulum to overcome friction and keep moving to the end of its swing. Oh, and if you're wondering about this small clock face here, it allows technicians to keep track of the time on the tower's giant clock. Imagine having to run down the tower and into the square to check it every day. Okay, so the seconds are ticking by perfectly. But how does that turn into this? A series of metal rods connect the mechanism to the clock. The muscle to move the giant hand comes from a hanging weight. Same idea as the one on your grandfather clock. When the weight falls, this cable turns gears, which turn the rods, which turn the hands. And that sets up the machine's third challenge. How does the escapement keep the whole thing from spinning out of control? It counts out the seconds, and after 60, lifts a release arm that's been stopping the weight from falling. The weight is released for a fraction of a second, just long enough to turn the gears that turn the hands. This repeats every minute. As the weight nears the end of its run, a small motor winds it back up to the top to start dropping all over again to power the clock. But there's one more challenge. In making timepieces this big, clockmakers created a problem. Bad weather pushes on its hands, which transfers back through the gear train. The heavy weight can resist the force, but can damage the escapement mechanism. So they installed a mainspring called a remontoire that drives the escapement, which powers the pendulum. When the weight falls, it rewinds the spring. This gives the escapement the power it needs while isolating it from brutal forces outside. So there you have it. This is what makes a giant tower clock tick and talk. All right, now let's check out the Glockenspiel. On level 9, a supersized version of your grandma's music box. It transforms individual notes from a song into electrical signals with these metal pins. Those signals control the gears on this table that yank long cables that in turn pull on clappers, clanging out classical tunes on 7 tons of bells. Each pin sends a note to each gear that plays a bell, and each bell plays its part. For these life-size figures on the 8th floor, which are driven by an electric motor and a set of gears. Jousting knights in one show, dancing barrel makers in another. And then a rooster pops out for good measure. It's a bit like an old cuckoo clock, only with more gears and bigger cuckoos. Floor show or not, it's the pendulum that counts on this machine. And you'll find it on every mechanical clock there is, cuckoo or not. This is the Peterborough lift lock, located an hour and a half north of Toronto, Canada. It's a pivotal linchpin of the Trent-Severn Canal, a 386-kilometer waterway that allows boaters to travel with ease between the Great Lakes. Built in 1904, it easily hauls 1,500 tons of water, equivalent to almost 1,300 passenger cars, from bottom to top in under 90 seconds. All without using a single watt of electricity. Okay, the control panel lamps are electric, but that's it. It's also the highest hydraulic lift lock in the world. Let's see how it works. Lift locks are built when a canal needs to get past a natural barrier, like a waterfall. That's where the lift part comes in. So, how do you do all that without motors or electricity? With help from gravity and water. This guy fires a piston beneath the lock to raise this gate on the bottom tub. This separates you from the canal. And that leads us to our first problem, lifting a giant tub. All it takes is water and gravity. The lift lock is like a seesaw. One side goes up, the other has to go down. But the top tub needs more weight to do that. An extra 30 centimeters of water flows in here. That makes it 144 tons heavier than the bottom tub. It uses water for weight because as far as this machine is concerned, you and your boat are weightless. As your boat floats, its total weight displaces its equal weight in water. So no matter how many boats are squeezed in, the weight never changes. Okay, so we're moving thanks to that extra sip of water in the top tub. But how exactly are we moving? What's preventing this 2 million liter bathtub from smashing straight down into the canal? Two identical rams riding on a cushion of water. The rams move inside these cylinders called press wells. As the top tub descends, it drives the ram beneath it down. Water in the press well is then forced up this narrow space and channeled through a connecting pipe to the other side of the lift lock, where it forces the second ram and the tub on top of it up. When the ride is over, the guy upstairs shuts off a valve located in the center of the pipe that joins the two press wells. This locks the tubs in place, and you're free to fire up your boat and motor away. It may be old, but the engineers that built the Peterborough lift lock knew a thing or two about green technology. Water and gravity. Simple. A century on, still the highest hydraulic lift on record. Major daily newspapers in London, New York, or Paris have only a few hours to print over 1 million copies and get them on the street. And they couldn't do it without the web offset printer, a machine that prints non-stop from feeding to folding without a smudge. It's called a web offset because of the configuration of paper paths. For newspapers, it's the fastest and cheapest form of high-volume commercial printing. 11 kilometers of paper in just 40 minutes, changing the rolls on the fly without stopping. The paper runs through this printing stack at up to 10 pages per second. And these rollers are the key to the machine's ability to spit out such high-speed precision. Here's how it works. The actual printing plate is a flexible aluminum sheet that wraps around a drum. But on a closer look, that's a smooth surface. How does a printing plate make an impression with no raised edges? It's based on the fact that oil and water don't mix. A special coating on the aluminum plate is designed to absorb oil-based ink. So, if we ink this plate now as it is, it would produce solid black. So, ultraviolet light is used to project a 4-page digital image onto the plate's coating. The parts exposed to the UV light harden in place, while the unexposed parts of the coating dissolve away in a chemical bath. Emulsion and bare metal now form a printing plate. Once loaded on the print cylinder, the plate collects ink and water from rollers. The hardened sections of coating absorb ink. The other parts of the plate take on a film of water that keeps the non-printing areas ink-free. So, the ink-coated plate is ready to transfer, but not directly to paper. That would wear out the plate too quickly. The metal plate is wrapped around this drum. The ink image is offset from the plate to a rubber roller called a blanket, and the rubber then transfers it to paper. That's why it's called offset printing. Now to print both sides, the paper is sandwiched between an opposing set of plates and rollers. With a 4-page printing plate on each side, one turn of the drum produces 8 pages in 1/10 of a second. It's all black and white. But what about photographs? How does this machine print gray? Well, it can't. But here's how it works. A photo is filtered through a screen, and the gray tones are broken down into black dots called halftone. The closer together the dots, the darker the effect. Pull back, and the halftone image appears as gray. We make up color the same way. When you mix black and 3 primary colors, cyan, magenta, and yellow, you can create every color that exists. The original color image is split into 4 halftone plates. 3 plates carry one of our colors, and the 4th carries black. The color inks are loaded into the machine. Then, the plates are printed one after the other with halftone dots. And as long as they are perfectly lined up, our perception once again connects the dots into a continuous tone. This press has 6 printing stacks. The tall stacks have 4 sets of drums so they can print in full color, and the smaller ones just print black. The web of paper feeds through the stacks from both ends and meet at the collator. The machine collates, folds, and chops the newspaper, then sends it along to be stacked and bundled at over 500 copies a minute. The web offset printer set the standard for hot off the presses. Even in today's digital age, nothing can beat this machine for volume, speed, and cost.